So this is the first question from last year's Stellenbosch camp in the advanced test. It's was also in the intermediate test because we're too lazy to set, 10 unique questions for the intermediate and advanced test. So the last two questions in the intermediate test are almost always the first two questions in the advanced test. So if we'd got into this yesterday, I wouldn't have to do it. Well, I suppose there's no such thing as I have to do this now, but then I wouldn't be doing this now. I just tell you to watch the video from yesterday that doesn't exist because I don't know how Twitch works. Yeah, it is what it is. So the question is, how many ways are there to choose 24 black squares from a standard chessboard, 32 black and 32 white squares alternating, in case you don't know what a chessboard is, such that exactly 3 squares are chosen in each row and column. So this is a chessboard. 2, 3. Ah, I guessed right. That is 8. Amazing. Uh, okay. And let's they shaded alternating like this, so that there's 4 black squares in each row and in each column. And we want to choose 3 of these out of each row in such a way that there's also 3 chosen in each column. So we can't just blindly go in and pick a random 3 in each row, because then we might be unlucky and, always choose the first black square in each row. And then the first column is going to have 4 chosen black squares in it instead of 3. So that approach is going to fail. Uh, and this is me demonstrating that if in preschool, when you were sitting coloring pictures, you asked, when am I ever going to use this in life? The teacher should have told you, because you're going to become a Twitch streamer and color in squares on a chessboard while explaining maths. And because you were in preschool 20 years ago, you'd be very confused because Twitch wouldn't exist yet. But this is me demonstrating that I passed preschool. I can color in approximately in the lines. Okay, and we want to choose 3 in each row and column. And like I said, we can't just go in blindly and just always pick 3 however we wish, because if we pick those 3 and those 3 and those 3 and those 3, then we have a problem, because now we've picked 4 in this column. So let's not do that. Instead, the insight here is that in a lot of counting problems, it's a lot easier to sort of count the negative version of something. Like, you might be familiar with the fact that I thought I changed the color back. No. There we go. That n choose k is equal to n choose n minus k. Because choosing k objects is the same thing as choosing which n minus k not to pick. If you haven't seen this notation, then please say something so I can explain, because the point of the session is partly so that you can learn things. So here, because objects out of n is the same thing as choosing which n minus k not to choose. That's a weird sentence. And the same thing same sort of idea might make this problem easier. Is choosing 3 black squares out of a row is the same thing as choosing which one not to choose. And in each column, we have to have one of these not chosen black squares. So there can't be two of these in the same column. But basically, that's the only restriction. Every other choice, as long as we pick one in each column, we know that that column is going to, we know because we're leaving out one black square in that row, the row automatically has 3 black squares in it. And because we've chosen one in each column has 3 black squares in it. So we want to place one red X on a black square in each column. And the number of ways to do that is exactly the same as the number of ways to choose 3 black squares from each row in such a way that it's not just one in each column, it's one in each column and row. So we want to place one in each row in such a way that there's one in each column. More precisely. Right, does that make sense? And you can see why that's going to give us what we want. So if I place one in this row, maybe, and this one, there's one in that column, and in this row I haven't used this column yet, and in this row I haven't used this column yet. And you can see here I've now got, because there's an X in each row, there's 3 black squares, 3 non-X'd black squares in each row. Because there's a black X in each column, there's 3 non-crossed out black squares in each column. So now the question is, in how many ways can we do this? And you can consider the odd and the even rows separately because they sort of create their own little subgrids. So if we just look at these rows, they have black squares in the same columns, but they don't have, they're completely disjoint from the other, from the even numbered rows. And the same thing's going to happen with the grid I'm now going to draw in purple. Right, so we've got these 2 overlapping 4x4 grids, and in each one, we want to do the, well, we're solving the same problem essentially. We want to place a black square in each row in each row in such a way that there's one in each column. So in the blue grid, how many choices are there for where we place this red X in the first row? Anyone? It's not a trick question. I might ask trick questions, but this isn't one of them. So in this row here, how many choices are there for where we place the red X? Well, you can place it on any one of the black squares, and there's 4 black squares. So it's 4 choices for where the red X goes in the first row. And then in the second row, we can now place it in, or in the third row in the original grid, but the second one in this blue grid, I think. there are three choices because we can place it in any one of the black squares, but it can't be in the same column as the first red X that we've already placed. For where red X goes in second row, because it can't be in the same column as the first red X. The same thing, same idea works for the third blue row. Third blue row, which is the fifth real row. It can't be in the same column as the first two, and then the last X, once we've placed the first three, so once we've placed that one over there, this one over here, and this one over here, this one's forced to be in the only remaining column. So there's only one choice for the last blue red X, which sounds weird because blue is not red. Okay, which gives us 24 in total. Because you multiply these, because for each of the four choices in the first row, there's 3 in the second row. So, so if we place it here, there's 3 options for where the second one goes. And then if we place it here, there's another 3 options for where the second one goes. And if we place it here, there's another 3 options for where the second one goes. And if we place it here, there's another 3 options for where the second one goes. So in total, we've got those 3 options 4 times. And that's why if you've been confused about why you multiply when you have these kinds of chains of choices to make, that's why it works. It's because for each of the 4 choices that we have here, there are 3 choices. And for each of those, there are 2 choices. And for each of those, there is 1 choice. So there's 24 ways in total to place the red X's in the blue grid. And exactly the same logic, so I'm not going to repeat it, tells us that there's 24 ways to place the red X's in the purple grid. Okay. And because these are sort of independent, every valid choice of the X's in the blue grid and the purple grid, because they don't share any, because none of the columns in the blue grid overlap with the rows or columns in the red grid, at least in the blue grid and purple grid, at least as far as the black squares are concerned, there's no interaction between them. Every valid allocation of red X's in the blue grid and valid allocation of red X's in the purple grid gives a valid allocation of the grid overall. And so again, we can multiply them because for each way of choosing how to place the X's in the blue grid, if we make the first choice for how to place them, there's 24 options in the purple grid. If we make the second choice for how to place them, there's 24 options in the purple grid, and so on. Each time there's 24 options, and so there's 24 times 24, which is a number. I don't have squares memorized that far. So thus, there are 24 times 24 ways in total. Well, it's 25 squared minus 50 plus 1, and 25 squared 625, so this is 576.